So I will now give the floor to Dr. Vissarion Papadopoulos, who is also professor at the School of Civil Engineering of NTUA, the National Technical University of Athens, and a founding member of the Multi-Scale and Multi-Physics Research Group, the M Group, and will give us a presentation on data-driven computational mechanics at exascale. The floor is yours.
Thank you very much, Ilya. And I would like to thank the organization, the organizers of this event, very important event for the area of computational mechanics. I could not have a better introduction to what I'm about to present to you. Other than what my mentor, Professor Papadrakakis, delivered to us a few minutes ago. I think it was an ideal introduction of what I am about to present. And I would like to share my screen. Just give me a second. Can you see my screen now?
Yes.
Yes.
All right. Thank you very much. So I will be presenting a topic on data-driven material design at exascale, which is part of the DCOMEX project. This is a Euro-HPC funded project which runs with the collaboration of a number of partners, including GRNet. And the goal is to fuse machine learning and data-driven methods with large-scale linear algebra solvers to solve extremely demanding computational mechanics problems. The aim and the target in terms of product is to deliver an integrated open-source, user-friendly, customizable computational mechanics framework that harnesses the capabilities of next-generation European exascale computing architectures. Therefore, this joint effort in the framework of the Euro-HPC is expected to provide with unprecedented advances to the field of computational mechanics. Partners of this project is NTUA, ETH, TUM, University of Cyprus, and as I told you, GRNet. The main objective of the call is to construct the so-called AI Solve library, which is an HPC supported and AI enhanced linear algebra library for computational mechanics. This includes the development of a set of innovative machine learning methods for dimensionality reduction and surrogate modeling, including diffusion maps and convolutional autoencoders. You will see later some slides on this. And then develop the basic AI Solve idea, which is a library that fuses data-driven methods with efficient block iterative sparse linear system solvers. This is an idea that merges the two worlds, the worlds of data science and computational engineering modeling science, in the sense that it utilizes the tools of both worlds to combine, to propose a combined methodology that accelerates the computations at the various levels of accuracy. It can also be seen as a multi-fidelity kind of approach, which merges the physics-based world with the data science world. Then, in this framework, we integrate Solve, which is a core finite element solver, open source solver, with Corally, a core UQ uncertainty quantification engine, and deploy it in the exascale environment provided by the EuroHPC facilities. Of course, we have to talk about our applications, which is bioengineering, which is about the bioengineering problem, an optimized patient-specific cancer immunotherapy problem. This is a really complicated multi-scale, multi-physics problem, and of course, a very well-known multi-scale material design. You can see an overview of the framework at the center of this tool. Let's say we have the MSolve core finite element solver, which is orchestrated by the Corelli framework in order to perform uncertainty quantification and optimization in high-performance computing environments, such as the CSCS Pittsdale machine, Meluxina, and possibly other. We will deploy it on ARIS as well. Actually, we have started this effort quite a few months ago. And here is the integration. The Corelli is the main scheduler, the orchestrator that distributes the jobs to the workers. Each worker utilizes the AISolve library, which in conjunction with EMSolve gives back to the Corelli the prediction of the responses that is required to proceed with the UQ quantification, the certain quantification or the optimization steps. And the basic applications, as I told you, is patient-specific cancer immunotherapy treatment. This is a coupled multi-physics problem that involves a number of equations, solid equations, advection, reaction, diffusion equations, all of them coupled in a finite element modeling framework. And on the right, you can see a material design problem, which is of great interest, as you may all know, to various industry. Both problems are extremely computationally expensive. This is the reason we have initiated the effort of constructing this AISolve in order to overcome the computational barriers. As I told you, we need to go definitely to exascale computation. The way to accomplish this exascale performance is to combine data-driven methods with high performance computing, and in the framework of efficient finite element solvers. And this combination of all above is attempted in the framework of this library called AISolve. Now, regarding the first pillar of this library, our data-driven and machine learning philosophy, let's say, I will review it in a couple of minutes. As you all know, all the physics of engineering problems are encapsulated in various laws like Navier-Stokes, 3D elasticity, heat transfer laws, conservation laws. And after this discretization, using some kind of numerical, let's say, procedure, for example, finite elements, you always end up solving this system of PDEs through the solution of a linear system of equations. This is exactly what Manolis Papadrakakis explained in the previous lecture, the previous presentation. when we're talking about large-scale systems, detailed systems, the finite element models, modeling, the responses are require the solution of this linear system of equation, which is always in the form of inverting the stiffness matrix of the system, which in case of large system dimensionality, this is an extremely computational demanding operation. And moreover, if this analysis has to be performed in a parametric, let's say, problem environment, such as UQ or optimization, or even more transient UQ optimization problem, this is a solution that has to be solved a number of times, for example, 10 to the 10th times. So it is a really, really computationally demanding problem. And here you can see, let me just use the spot. So you can see the framework of such parametric analysis. And in order to tackle this problem, you have to reduce the time, the computational time required to deliver the finite element results. And how do you do that? Through surrogate modeling as a first step. So you replace the detailed model with an equivalent AI model that delivers the response at significantly lower computational time. Sorry about that. Okay, so what is the philosophy, our philosophy of doing that? We use convolutional autoencoders, which essentially project the dimensional space of our solution to a latent space of a low dimension. This is a lower dimensional space through pooling, which consists of a number of convolutional pooling layers, the deep neural networks, in fact, and then a decoder, which essentially performs the opposite operation and transforms the latent space to the original one. All these, let's say, procedure is controlled by the minimization of the mean square error in the classical sense that machine learning methods work. In the framework of the parametric analysis, if we have the parametric space represented by a few variables, let's say stochastic or optimization or design variables, then in order to predict the solution space, which is the high dimensional space, instead of doing a direct analysis, which is a nonlinear, for example, the transient analysis, we use the decoder and predict the value of the mapping of the parametric space to the latent space, and then use the decoder to go back to the initial solution phase. Of course, there is always a training phase on this, which is also the cost involved to such analysis. And here you can see an example of transient analysis, a nonlinear dynamic analysis of a 5-story metallic frame building. This involves a number of random parameters, namely the modulus of elasticity and the Helix strength of the material law. This is a plasticity, classical plasticity model. And also the earthquake is random. This A parameter is random, which is the directionality of the earthquake. And using exactly the procedure that I mentioned, you can see that we can establish very, very accurate predictions of the response with errors that are less than 2% in all cases. And here you can again see the gain in the computational cost. On the left, you can see a comparison of the surrogate approach with the direct Monte Carlo approach when we have a few Monte Carlo samples, 3,000 for example. But this relative gain is more significant as we increase the number of samples that you can see on our right. So for, let's say, 200,000 simulations, we can have a gain, a significant gain. So from a 68 days, we can reduce computation to only 5 hours in an i7 laptop computer. Again, we can use machine learning, the DNNs, to train constitutive laws and use them instead in a FP-square analysis procedure. And this can be done either in one scale or in many scales when we have materials that operate in a number of distinct length scales or time scales, if you involve also transient phenomena. And if you do an optimization in such a material that involves, for example, more than 2 scales, and you need to optimize the material and the structure, as in the case of reinforced concrete, for example, then you would need 10 into the 7, for example, model evaluations, and from 2,000 to 5,000 training samples at each level of hierarchy of the material that is delivered. So even if you use AI for the training set, you need a large intractable number of computations. So AI is by itself not enough, both because in very computational demanding problems, the training phase can become intractable, and as well as because in many cases the predictions are not satisfactory, so we need to improve the accuracy. Therefore, we have foreseen that there is always a need for a synergy between AI and high-performance computing. And when we are talking about high-performance computing methods, we are talking about solvers, and namely domain decomposition solvers, primal dual methods introduced by our mentor Papadopoulos, whose ideas we always follow, and multigrid methods, algebraic and geometric multigrids. And I won't stay in this domain decomposition preconditioners because I don't have time. They can behave really fast and accelerate significantly the solution of the problem in a parallel computing environment, because I want to describe the philosophy of the merging of the AI solve with iterative solvers in the framework of algebraic multigrid. So in algebraic multigrid, we have a restriction operator that reduces the original dimensionality to a lower dimensionality space, and then the prolongation operator. The idea was that this is a similar approach of dimensionality reduction. So we used the training phase of our surrogate model in order to construct the restriction operator. So just performing a POD on the samples with which you train the neural network, for example, or the autoencoder, you can construct a POD basis upon which you can base the restriction operator of an algebraic multigrid solver. And then you can perform a very, let's say, refined procedure with much reduced iterations in the framework of multigrid, as I will show you. So the AI solve ecosystem is constituted. Now, before I go to these slides, I want to show you. So I will stay here, describing a little bit the AI solve ecosystem. It consists of machine learning, high-performance computing solvers. And then all these technologies is fed into the iterative solvers, which is supported by sparse matrix vector multiplication kernels, and as well as communication optimization frameworks. And they deliver the results that I promised. So I will finish in 1 minute. For example, in a coupled problem, a porous media problem, the classical bio problem or soil mechanics, where we can have 2 model parameters being random. This is a 40,000 degrees of freedom problem. You can see here the performance of our AI-enhanced multi-grid solver, which is also enhanced as with the initial solution of the autoencoder that I just described you. So we are starting the iterations from the solution that we derived from the machine learning procedure. And you can see that we can achieve very, very significant speed-ups, which are very pronounced at the levels of accuracy of the order of the 10 to the -5 and 10 to the -6. You can achieve a speed-up with respect to classical multigrid of 76 times for an accuracy of 10 to the -4. So I think I will stop here. All the results of the problem will be published and presented in upcoming conferences. And please, if you're interested, let me know, and I will let you be informed with our progress. Thank you very much.